All right, hello. If I cut out, just shake your hands wildly around, and I'll try to be more direct in speaking. Thank you so much for coming out here. This has been a really interesting event, really exciting. It's been really wonderful to meet all the veterans and their families. It's been really wonderful to see these talks from historians, from the government, from the senator. It's just been a really exciting event, and I'm really pleased to be here. I've been asked to talk about innovation and the Manhattan Project, a crucible for innovation. As you know, they had to develop a lot of new inventions, a lot of new techniques, a lot of new science, a lot of new technologies to make the atomic bomb. What I want to talk about a little bit today is the scale. How do you get 3 atomic bombs in under 3 years? It's not just equations on a chalkboard. This is, I think, one of the persistent popular visions of the Manhattan Project. It's that Oppenheimer gets up and he writes E equals mc squared, and they say, my God, you're right, and then they have a bomb. As the people who work in here, the people who talked yesterday, the people who are talking today know very well and emphasize very well, that isn't the case. There is a role for theoretical physics. I'm not downplaying that. But a lot of it is work that's diffused much more widely, and many more people and much more money and much more of an effort than even people who know a lot about the Manhattan Project or participated in the Manhattan Project even know, I think. So I'm going to talk about how it worked, and also how improbable it was, how improbable its success was. Because it's one of these stories where we know the answer, we know what happens, we know it's successful, it's easy to tell it as a story of like, of course it worked, of course it was good ideas. And there are so many junctures along the way that could have delayed this project by just enough time to make it not actually be useful for the war, to not actually be successful. To not have the atomic bombs ready for the invasion of before the invasion of Japan is a couple months of time. How many bad mistakes or bad calls do you need to be a couple months off in any big endeavor? Anybody who's tried to run a project or get a bill passed by Congress will know the answer is to that one. This is the state of nuclear fission research in 1939. This is the actual table with the actual apparatus on it of the Hahn-Meitner-Strassmann experiment in Berlin. This is kept at the Deutsches Museum in Munich, and it's a pretty big table. This is a nice table, but it's tabletop science. This is what they use to discover nuclear fission, this in their brains. It's not a bomb project. You can take the results of this and you can go and say, well, maybe nuclear bombs are something to worry about, but no amount of work you do on a table is going to make you an atomic bomb. It doesn't work that way. This is a picture of the state of fission research in 1945. So this is from the Manhattan District history that Cindy mentioned, which is, much of it has been declassified by the Department of Energy pretty recently, finally. And this is how the military viewed the Manhattan Project. So we have our big sites that we know about, Hanford, Los Alamos, Oak Ridge. They're important. We have some of the big university sites that we've heard a lot about here, Berkeley, Chicago. And we have some sites on here that a lot of people don't know about. What's in Alabama? It's a heavy water plant. What's in Grand Junction? Well, that's how they coordinated the uranium mining they were doing in the Southwest and milling. What's in Decatur? That's where they're making the barrier for the gaseous diffusion plant, and so on and so on. And already, this is more sites than most people are used to thinking about for the Manhattan Project, because we usually think of the 3 big sites and maybe 2 of the big universities. Even this just scratches the surface. I've been making a map. I'm going to put it online pretty soon. I say making a map. I was working on this a little bit over the course of many months, and then I decided I should have this ready by the time I give a talk. So I've been doing this over the last weekend. Of every Manhattan Project site I've been able to find a reference to. Every office, every laboratory, every factory that was subcontracted to extrude uranium metal into some weird shape. And this is still a work in progress. The one I'm going to put up on the internet is going to be interactive, so you can click and zoom and see all the details. But here's where we are as of this morning. So these are the Manhattan Project sites that I've been able to find. This database contains over 230 of them. These are only North America. I've left out Tinian. I've left out, they had a site in Africa. I've left out the United Kingdom. I've left out their Paris branch for Alsos. I've color-coded them. The sizes are somewhat arbitrary. They're kind of arbitrary importance. I just made Los Alamos bigger and Oak Ridge bigger and Berkeley's bigger, and don't attach a lot of importance to that. The colors are interesting, though. Orange is government or military or various forms, so you can see quite a lot there. These are both branch offices, naval ordnance depots, naval research centers. Green are universities or colleges or other educational sites, of which there are many more than I was aware of. I knew that they had a lot of research all over the place, but every once in a while I'd find a reference to a place I had no idea had a major role in the Manhattan Project. They were doing research on fluorocarbons, or they were using a particle accelerator to find out about the neutron spectra and sending the results back to Los Alamos. And blue is private company and industry, which is by far the overwhelming number of sites. Some of these are major, giant corporations that still exist today. Some of these are small operations where they are contracted to make some part. And most of these places, even at the big sites, are people who don't really know what they're doing and to what ends. They've been told, make me a really specific gun barrel and don't ask questions. This is the sort of thing that when he came to this country, the physicist Niels Bohr said to have remarked, I told you it couldn't be done without turning the whole country into a factory. You have done just that. This list includes places where they refined uranium salts into oxides and oxides into metals, places where they researched fluorocarbons, barrier materials, places where they produced heavy water. We produced a lot of heavy water during the war, even though we didn't really use it. It was a backup plan in terms of reactors. We used some of it, but we produced a lot of it. Places where they produced polonium, beryllium, parts of the bombs. Places where they did nothing but move paper around. So University of New Mexico has an office on here. They didn't do that much at University of New Mexico, but they received all of the shipments from Caltech of explosives and forwarded them to Los Alamos, and they did this to help preserve the secrecy. And I think that that is part of the Manhattan Project. Could you have gotten away without a few of these sites? Sure, but we use them all, and even the ones that move paper are essential. And one of the ones on here where they did mostly moving paper, mostly talking on telephones, is the building we're in now, which is where Vannevar Bush's office was. The Office of Scientific Research and Development was located in this very building, and I don't know which office, but I bet they could tell you. And for me, it's mind-boggling to imagine Vannevar Bush and Leslie Groves, what their workday was. We imagine them always going out to the sites and, no, don't do that, do this. Most of the time, they're on the phone. Most of the time, they're sending letters. And they're moving this whole network of people and materials and money, and ultimately producing 3 nuclear weapons. It was a big, big project, bigger, I think, than most people know. It also had a lot of people. It takes people to make an atomic bomb. This is a chart of the employment. Usually when people talk about how many people are on the Manhattan Project, they say peak employment was 125,000 people. Which is true. In June 1944, there were 125,000 people employed as formal contractors on the Manhattan Project. The total employment is more like 600,000 people, which is a lot of people. How many? That's almost 1% of the entire civilian labor force of the United States in World War II. Had some role. And you might ask, wait, why is peak and total so different? Because they had very high turnover. Because most of the jobs in the Manhattan Project were crummy jobs. They were construction jobs or operating jobs where you were never told what you were doing, so you could take no pride in your work. And they were hard and underpaid, and they were in remote areas, and the people who were employed didn't have to do this. This is not the Soviet Union, right? They're not forced labor. And they would quit. And so some of these sites had a 20% per month turnover rate. So every time you see one of these lines go up and it adds a number 20,000 people or something, that's adding on top of a 20% loss for that month, which, again, I find just mind-boggling. This particular graph has a lot of detail on it. It's on my website. To make it a little easier, I've broken it out into some sort of basic categories here. So green here is the total employment. Blue is construction and design, and you can see very clearly how this project gets made. It's this very early phase, starting at the end of 42, and especially 43, of build, 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 build. And then it becomes people having to operate these plants. And the number of operators, I was very surprised, is extremely large too. I mean, construction makes sense, right? It takes a lot of work to build K-25, Hanford. But it takes a lot of work for people to run them as well. And so 66% of the people are at Oak Ridge, 23% were at Hanford, and 11% are spread among the rest. The number is actually probably even higher than this because these are only the formal contractors on the rolls, and a lot of subcontracting took place. A lot of work was done where they said, just ship me a bunch of uranium, and I don't care how many people are working on your project. So if you added everybody, I don't know how many that would be, but I think it would be even larger. So this is a pretty staggering number. Again, about 1% of all Americans not in the military had some role in the Manhattan Project. It also cost a lot of money. We all know the famous figure. It's about $2 billion. In 1945, $2 billion sounded like a lot of money. If you translate that into modern currency, it's depending on how you do the economic equation, because a Manhattan Project is not a loaf of bread, so a consumer price index is not always the best way to do it. It's between $30 and $100 billion in modern currency, which unfortunately does not sound like that much, because we are really used to spending tens of billions of dollars on a new weapon. I looked up the price, I don't want to be political, but of the F-35, and it's like significantly more than that for one fighter plane model. But that's a lot of money. This is a chart of monthly expenditures, which I really like, and you can just see how they start relatively modest. You know, a few $1 million a month, that's still pretty, you know, if your name is on the responsibility for it, that's still a lot. And then they're getting up to spending hundreds of $1 million per month. This is, I think you could correlate this graph with the amount of stress that General Groves has. Especially the cumulative price on the Manhattan Project. I think it's even, I don't think it ever goes down. I think it goes up, 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 up. Now this isn't a totally unheard of amount of money. It's about 0.1% of the US GDP during World War II, which is pretty big. That's impressive. The B-29 program cost about $3 billion, but they produced a lot of B-29s. The V2 program of Nazi Germany produced about this much money, about the equivalent. So it's on par with big weapons programs for World War II, but it's still a lot of money to produce 3 bombs. They kept okay records on how they spent the money. Groves was very worried about being audited by Congress for the rest of his life. And so he kept a lot of records. This Manhattan District history, which all these figures are coming, all this data comes out of, is a testament to how worried Groves was about sitting in front of Congress for the rest of his life. They didn't keep track of everything, but I really like that they kept track of every month's expenditure down to the pennies. Very General Groves thing to do. And here I want to just show you the real miracle of the Manhattan Project. We go all the way down to the total. Oh, it's hard to see on this, but they managed to make it round to the nearest dollar. I'm sure there was no accounting fudging going on. I'm sure it just 1 in 100 chance. And how did they spend this money? They spent a lot of it on Oak Ridge, as people at Oak Ridge probably know. 63% of it went to Oak Ridge. 27% of the entire budget went to K-25, and 25% went to Y-12. That's incredible. I'm glad they worked. Hanford has 21% of the budget itself, and then everything else carves up little percentages of it, as you can see up there. Again, I'm also impressed. I don't think many people know this, probably in this room a number of people know this, but the amount of money we spent on heavy water production. We built 3 entirely new installations to make heavy water just in case we needed it for reactors. And it turned out we didn't really need it for reactors, but just in case. And that really sums up a lot of the spending on the Manhattan Project. Did they know that K-25 was going to work? Did they know that Y-12 was going to work? Did they know that Hanford was going to work? No. So they did all of them. It was actually very late in the project when they realized that you could take the feed from K-25 and send it into Y-12. That these didn't have to be competitors. They could be complementary processes. And it took all of these methods, all of this money, again, to end up with 1 uranium-fueled bomb and 2 bombs fueled by plutonium, 3 if you count the one that they almost had ready to go. So all of this money, most of it goes into producing the fuel for the bombs, which is, by the end of the war, it's about 30 pounds of plutonium and about 140 pounds of uranium. So you just imagine all that map of all the facilities and all of these thousands of tons of raw materials going in and these lumps coming out. And that's the only byproduct. So it's otherworldly. And I don't know if anybody who worked on the project ever had to deal with this man. I hope not. Captain Robert Lavender. He has a great name, Captain Lavender. He was a retired naval attorney, and he was the patent advisor for the Manhattan Project. And so this is just another way to think about how big and what they were doing was. They had a massive patent program that Vannevar Bush put into place. Vannevar Bush got the idea very early on with James Conant, his friend and advisor, that they did not want individual scientists to own their work on the bomb. That the government was paying for it, so the government should own it. This was like partly ideological. They believed that if the American taxpayer paid for it, the American taxpayer owned it. And part of it was control. Because if a scientist owns something really important, maybe the scientist gets to tell you what to do with it. And they didn't want that, surprisingly. So they had patent lawyers going to technical meetings at the different sites. They had patent lawyers going around and looking at every report, every notebook that was being made. They even sent somebody specifically to the Trinity test to verify and be an official witness that they had reduced it to practice, which I really find lovely, the jargon of the patent attorney intruding in on this story of making atomic bombs. So what did they do? Just to put this perspective, these numbers. How many technical reports? 8,500 technical reports. They looked at 6,300 technical notebooks. They docketed 5,600 distinct inventions, which just gives you an idea of how much production and innovation and development was going on. Again, they weren't just building atomic bombs. They were building all of these other things that you need to get them. And that's in 493 different subject classes. So that's 493 distinct areas of technical development. And they approved how many patent applications? They ended up approving 2,100 for filing immediately after the end of World War II. Now, these were secret patents, which, if you're a patent attorney, sounds like a contradiction. Usually a patent is something public. You can go to the patent office and see it. They obviously didn't want that to be the case, so they kept them secret for a long time, and there's mechanisms in place to do that. And just to put these into perspective, if this 2,100 patent applications, that's 1.5% of all patent applications in 1946. So over 1% of all of the patent applications at the end of World War II were secret Manhattan Project inventions. They aren't making a bomb. They were making an entirely new industry from scratch. This is a patent pool that's larger than some of our more innovative industries today. And they did it while trying to win World War II, and they did it entirely in secret. They ended up releasing some of these technologies later. So the way the procedure worked was this application would stay in a secret safe, sometimes at the patent office, sometimes at like Los Alamos. And if down the line they declassified the underlying technology, then they would look at the patent application again and say, oh, is this a good idea if we're already releasing it publicly, should we grant the patent? And so then they would evaluate it, and then if the patent office agreed it was a novel invention and they'd done all the paperwork right, they would stamp, this is a patent on it. So they have they're actually very easy to identify, both because they've been signed over to the government and the names of them are people we know, but they have big gaps in the date of filing and the date of granting. So they would file for the patent in 1944, but then the patent gets granted in the 1970s. That's not usual for the patent office, even with their inefficiencies. So just a couple examples of these. I put the patent next to the actual picture of the invention, just so you can see the difference between how a patent lawyer sees an invention and how they actually look. So this is the patent for the nuclear reactor. It's one of many patents for the nuclear reactor, but this is the big, fat one that covers the basic technology. It's listed to Enrico Fermi and Leo Szilard as a neutronic reactor. They filed for it in 1944, and they granted the patent in 1955. So 1955 is Atoms for Peace and the declassification of reactors. So it was secret for 11 years. This patent is really pretty interesting. One little aspect to it, Szilard, as you know, by the point in the Manhattan Project when they're starting to rustle up these patents, he's no longer a friend of General Groves, to put it mildly. General Groves actually wrote out an order that he could intern Szilard if he wanted to. He actually wrote it out. I think we should lock this man up until the end of the war because he's dangerous. And they didn't file it. He showed a little restraint. But Szilard wasn't signing over the rights to the government on the reactor patent. And they basically, the government said, look, you can either sign this over now and just keep doing whatever you're doing even though you irritate us, or we'll kick you off the project and maybe put you in jail. And if we kick you off the project, you're not going to influence anybody, especially because you'll be in jail. And so Szilard finally signed it. If Szilard had controlled the technology for nuclear reactors, think about how powerful Leo Szilard would have been both in the war and the post-war. Also, we sometimes think of the government and the Manhattan Project and all of these people as being sort of all-powerful. And they had some power, they knew this, but they also knew the limits of their power. The patent system is in the US Constitution. They knew that if they abused the patent system during the war, the Supreme Court would eventually find out about it. And so they were very careful. They wanted all of the legality of this project done very smoothly. So they only made threats not on paper. This is another patent. This is for Glenn Seaborg, Arthur Wall, Emilio Segre, and Joseph Kennedy. And it's the basic chemistry of how you take spent fuel from a nuclear reactor and you make plutonium out of it. Kind of a valuable idea. So this is how they see it. It's this big flow chart. This is page 1 of many of the flow chart. And again, none of these patents are secret. You can look them up on Google Patents if you want. And this is kind of what that looks like on the left. This is one of the famous canyons at Hanford where they would do all of these chemical processes with acids and other bad things. So they filed for this patent in 1945. It was secret until 1965. So it's a 20-year gap. That's pretty secret. This is another interesting patent. These scientists, when they figured out all this chemistry, this was before they had gotten onto a government contract. They were doing this at the radiation lab in Berkeley, but they were not on an OSRD contract. And the result was it wasn't clear who owned this process. So the scientists said, I think we'll just keep the ownership because this is going to be worth how much money in the post-war? And the government, Vannevar Bush said, I don't think you're going to do that. And then the University of California said, actually, they did it while on our campus. Maybe the University of California should get a cut. So you get this wonderful tableau of we've got to win the war, we've got to work as fast as possible, we've got to keep going, and P.S., I want my patent rights. And you have all these lawyers and people, and Vannevar Bush invoking FDR and trying to claim this patent, and eventually they agreed to give it to the government, and it's a long saga. They got a sort of lump sum settlement later from the government, $100,000 a person for their work. It's not just the processes, it's also parts of the bomb. So things that we might think of as being so secret, why would they write down how to make it with no code names and put it in a safe somewhere? This is one by Alan Ayers called a pressure-sensitive switch. It's a barometric switch that detects altitude. So this is part of the firing system on the Fat Man and Little Boy bombs. It helps it tell when it's approximately at the right height to start going off. There's another switch that then fires later. So here's the Trinity device, the gadget. And I love this drawing here because you can tell it's the wiring harness of the Fat Man bomb. And it's even got the little casing in there. And the actual device are those little boxes within the X unit over here, this round part. And one of the really wonderful things is that the Atomic Energy Act of 1946 actually has a clause in it which says you cannot patent an atomic bomb, which is one of the funny aspects of U.S. patent law. If you get a primer on what can you patent, it's things like you can't patent perpetual motion machines, okay, and you can't patent atomic bombs. And I love these because they never explain why. And the reason is because of this patent program produced all these patents and Congress got very worried about it. So these patents never say you use this for an atomic bomb. They say if you just needed a switch that would maybe trigger something 100 meters above somewhere and happens to look like an atomic bomb casing, this is one way to do it. Some of these are really specific to the bomb. This is one, Donald Hornig was listed as the inventor, who I know a number of people here knew and worked with. Listed here as a low impedance switch. They call this now a spark gap switch. They filed for this patent in 45. They granted it in 76, so that's a 30-year delay. The longest delay I have is one that was filed for in 45 and granted in 89, or maybe even later, like the 2000s, well after the inventor had died. The inventor here, the name of the inventor doesn't matter because they don't get anything. This is just a legal nicety. It's assigned to the government. So this patent is really nice. It says if you need to send a high voltage signal to 32 different places with a tolerance of 1/10 of a microsecond, 10 millionth of a second, you could use the switch. I don't know why you'd want to do that, but maybe you need to have really high simultaneity for something. So this is part of the detonator for the implosion bomb, of course, right? This is a very important switch. I actually asked Hornig about this when he was still alive, and he had never been told that it was granted, and he had never been told his name was on it. And he was actually kind of surprised, and he said, I mean, I wasn't the guy who invented this. We were as part of a team. We all did this work. Who knows who the inventor is? And it doesn't matter because this is a patent lawyer document. This is not an official record for history or something like that. So one of the reports that the Patent Office wrote on us, they claim that they had filed patents on everything from the ore as mined to the atomic bomb itself. And I got really interested. Wait, did they really patent the atomic bomb, not just the switches? And the answer is yes. Those patents are still secret. They probably will always be. Even if they weren't secret, they could never be granted because, as I said, they prohibit patenting atomic bombs in this country. But I was able to get, through a Freedom of Information Act request, the names of the filing dates, the inventors, and the names of the patents. There's about a dozen patents. And so I don't know the details, but they're pretty fun to look at by themselves. So we have one, Robert Wilson, method and apparatus for explosive release of energy. Edward Teller, of all people, who knew? Method and apparatus for explosive release of energy. Robert Oppenheimer, production of explosive energy. Seth Nettermeyer, method and apparatus for explosive release of energy. John von Neumann, method and apparatus for explosive release of energy. Otto Frisch, fissile material arrangement. And there's more. This is just a sampling of about a dozen. There's some that we can figure out from the dates and the names and other references what they are. So there was one that I didn't include on here because it's a little post-war, which is an early H-bomb patent. This Teller one might be, I don't know. So we have this very bland legalese for how do you say atomic bomb to a patent lawyer. And so I think it's amazing. Somewhere there is a patent. It's in a safe in Los Alamos for the atomic bomb, and Robert Oppenheimer's name is on it. I mean, how more concrete can you get about being an inventor of the bomb? So I want to turn this over to the other panelists, and I want to make sure there's time for audience members, but I started out this slide with one of these silver pins, which I'm sure many of you recognize. These were given out to the people who worked on the Manhattan Project for over a year. There was also bronze pins that were given out for people, I think, for less than a year. If you look online, people always describe these as extremely rare artifacts. They're not that rare. You can buy them on eBay. Why aren't they that rare? Because a lot of people worked on the Manhattan Project. A lot of these pins were produced. I don't have the exact number, but it's way more than people realize. It's not a couple thousand at Los Alamos. We're talking about hundreds of thousands of people. I think keeping the sense of scale, how big it is, how many people it takes, how much money it takes, how many technologies you have to develop, keeping that in mind helps answer some of these questions that people sometimes have. How close were the Germans to getting the atomic bomb? They were nowhere close. They didn't have anything like this. This is a big program. This is a program of size. It's not totally unprecedented in size. The Soviet program had about 600,000 people on it too. Most of them are gulag slaves, but you know. But the one area where it is still unparalleled is speed. And that's really the thing to think about. This size of the project, could they have done it cheaper? Yes. Could they have done it with less people? Yes. Could they have done it in less than 3 years? No. That's what you need to produce an atomic bomb in, 3 atomic bombs in 2.5 months when you've never done it before. You have no idea which processes are going to work. You have no idea which problems are going to be on the horizon. No country other than has ever, even with modern technology, even with knowing all the shortcuts to take, even with espionage, even with knowing which processes work and which don't, no other country has come close to making an atomic bomb in that amount of time. This is still the world record for fastest atomic bomb ever created, which is amazing since it's the first one, right? This is the one where many mistakes were made, where many unknowns were still out there, and it's still the record holder. Again, they weren't making a bomb, they were making an entire industry. And when we look back, I think we need to keep that sense of it, and that sense of how close it could have been to not working. How easily it could have been delayed a few months if General Groves hadn't gotten the priority rating he wanted, or if the money had gotten slowed up, or if Congress had been a pill. Very easy to be off by 2 or 3 months in this, and very easy for it not to have happened at all. And so it's a pretty amazing thing. So, all right, when we look back, I think we should keep a sense of awe and not let it become, oh yes, of course we made the bomb. No, this is an amazing, improbable thing. All right, I'm going to turn it over to the panel, the others here, and then we'll turn it over to the audience. Thank you.
Thank you very much, Alex. We have a distinguished lineup here of people who were the awesome, amazing inventors. And we'll start with Ben Bederson, who was at Los Alamos.
I have to come over here because I want to look at the slides. I had the first slide I wanted to show is the same as your iconic picture of the main gate. It's a slightly different point of view of this glorified color picture. It's a dinky little shack. And everybody went through that one little shack with their white badges or their blue badges, with famous Nobel Prizes or PFCs like me. We all went through this dinky little shack. Can you hear me? Yeah. One of the unsung set of heroes, I would call them, in the Manhattan Project were the SEDs. Some of them are here. And SEDs are the Special Engineering Detachment. I mentioned them yesterday. They were really the junior scientists, the hands of the senior scientists. It's as if you were trying to run a university with just full-time professors. Nothing would happen. You need graduate students. And the SEDs were effectively the graduate students of the Manhattan Project at Los Alamos and Oak Ridge particularly. It's not working? Oh. This is one of the rare occasions that I can recall where we were in uniform and standing at attention. There was a time at the early stages of the Manhattan Project where we actually had to go through certain Army routines, such as inspections, that were truly hated. But that's I don't ever remember seeing an assembly like that, other than in the very early stages. Let me go back. Why doesn't it go back? Can you turn that back one slide? No, another one? Yeah. Speaking of all of the blind alleys of the Manhattan Project, here's one of the biggest ones called Jumbo. Many of you have heard of this. This was a huge vessel which was supposed to contain the test atomic bomb at Trinity in case it fizzled. Because if it didn't fizzle, we would have to evacuate New Mexico. I worked, when I first came to Los Alamos in January of 1944, I had not yet received my clearance, so I was put on this sort of low priority project to test container materials that would supposedly contain the fizzled atomic physics fusion bomb. But at a certain point, it was abandoned when it became clear that it was going to work. Now, I'll say a little bit about my own part in this project, in the Manhattan Project. I was assigned to Don Honig, just as you mentioned. Don Honig, he was a senior scientist. I think he was 3 years older than me. I was 24. He was probably 27. But he was a professor at Princeton in chemistry. His job, and therefore my job, was to develop the X unit that you just mentioned. And the idea was to develop triggers, electronic triggers, that would trigger 32 explosive lenses that would cause an implosion. We started from total scratch. And by that I mean literally scratch. I was given a laboratory. It was not at the main mesa because we were blowing up. We wanted to blow up things, and I and a civilian woman physicist. They call them girls, right? Margaret Ramsey. We were assigned to develop these switches. Our first attempt was simply to use two pins held together by plastic, and we tested them. Now, in order to understand how science works, you really, when you think about the history of the development of the technology of the atomic bomb, it goes back to the measurement of the speed of light, at least, because we had to develop an instrument that would measure the simultaneity of the application of switches, of 32 switches, within a very short time. And at that time, a short time meant a microsecond. Of course, a microsecond is not a short time anymore. We needed some way to measure the simultaneity of switches going off within a region of about 1 to 10 microseconds. Donald Hornig happened to know about such a machine that can do that, and he told me, and I think this is true, that there was a machine out at Caltech, and the machine was the machine of Michelson measured the speed of light, and in the Michelson-Morley experiment. The actual machine itself was shipped to Los Alamos, as it was told to me by Hornig. It may be that machine, or at least I'd like to think it was. It was just a camera that was capable of photographing processes within that short time. It consisted simply of a hexagonal mirror that rotated by a stream of air rotating around with a light beam hitting it and then sweeping across a photographic plate that was quite far away. And for just a simple device like that was used by Michelson and Morley, and we used it to measure the simultaneity of the switches. From those pins eventually developed the so-called X unit, which was a gaseous enclosed tube with electrodes inside. That's all it was. The next line. Oops, there we go again. I got very excited. I kept a diary, and the day after the first bomb was dropped, I excitedly wrote in my diary about the X unit. And about 2 weeks later, I reread the diary, and I said, "My God, what am I saying?" I was describing how it worked in my diary. So I happened to be a smoker at the time, so I just kept, I used my cigarette to burn out the secret part, the secret part of the diary. So my work as you might say, an SED graduate student, was typical of many of the other citizen soldiers, you might say, who were the backbone of the Los Alamos research activity. Here's Val Fitch, who won a Nobel Prize years later. I want to conclude this little talk with just a list of some of the scientists, some of the people who later became scientists, who were SEDs. Val Fitch, Arnold Kramish, who is a very distinguished science politician, Hans Courant, who shouldn't have been here. He's at University of Wisconsin. Dick Davison, who was a legend at the University of Washington. Richard Bellman, a mathematician. Tony Hoffman, who's the son of the pianist Anton Hoffman. Murray Peshkin at Argonne. Peter Lax, a famous mathematician at the Quran Institute at NYU. John Kennedy, who invented the basic language and became president of Dartmouth University. William Spindello became the officer at the National Research Council. Jesse Kupferberg, who started a high fidelity company that made famous amplifiers, and Jim Keck at MIT, and I should mention one more. There's one of my buddies right there, Bob Brown, who also worked with Hornig, and he's still sitting in the second row there. Anyway, when the ultimate history of the Manhattan Project is written, I think that the SEDs will play a more important role than now, where it is just barely in people's conscious. Okay, thank you.
One of Michael Vicchio, whom I mentioned earlier, had passed suddenly in 2005 and he started to try to write the history of the SED. He was dedicated to trying to do that. And anyway, we've taken all of his research and all of his interviews and things that people have sent him, and we're putting it online. It's all going to be under our profiles. We have 2,000 done, but we have thousands more to go. As I don't think we'll get to 600,000 people, but there were a couple thousand SEDs that we at least will do our best. Anyway, next is my good friend Jim Schoke, who was he was called after he got out of his work on the Manhattan Project as an inventor, and he made a business that was so successful. He was written up in magazine, and it was captioned "The $1 Million Baby." So, Jim,
the business was called $1 Million Baby.
The business.
At any rate, again, I'd like to express my gratitude and thanks for having been selected to be in the SED of the Corps of Engineers and assigned to the work on the Manhattan Project. Excuse my dementia, I have to refer to notes. My first assignment at the University of Chicago Metallurgical Laboratory, I was told that men were pilfering uranium, which at the time was called T-metal on the project. They didn't call it uranium. Tube metal, actually. The T stood for tube because the uranium was machined into rods, which was clad in aluminum, and into rods about that long and about an inch and a half, if I recall, in diameter. And they were used for fuel in the pilot reactor at Oak Ridge for developing the process for producing plutonium. At any rate, people who were machining the uranium, it was a very interesting metal because it was treated as if it was very valuable. It was heavy, very heavy, and when they machined it, it threw off sparks because it oxidized very readily. So obviously it would make a nice something to remember the project by taking it home. So people were putting chunks of it in their pocket and walking out of the security gate with it. And I was asked to develop an instrument to detect these chunks of metal as they were being walked through the security gate, which I did. And it worked. Of course, it made a great paperweight, you know. And there was one interesting story. One man who was one of the machinists, kept setting off the alarm every time he went through the security gate. And they searched him every time the alarm went off, and they found nothing. he wasn't taking any uranium, actually. So they finally decided to have him change clothes. Oh, by the way, when they were on the project machining, they had to change clothes to work clothes when they came in. Then before they left, they had to shower and change back into their civvies. And any rate, so they decided to have him take his clothes one at a time and put them at the security gate. And he, I'm sorry, yeah. At any rate, he kept walking through the gate, and finally they found that it was his belt that was radioactive. He was using the same belt with his work clothes as for his civvies. And so that was the end of that problem. By the way, they did find people with the equipment also who were taking chunks, or trying to take chunks home. Then I got another assignment to make a special filtered amplifier for one of the top physicists. I think it was Dr. Dempster. I didn't know what the amplifier was for, but I knew that it was supposed to be a tuned amplifier, meaning it only passed certain frequency, a narrow band of frequencies. And that frequency that it was supposed to be tuned to was 60 hertz, which is the standard power line frequency, a very low frequency. And so the electronic items that were needed for making a filter, a tuned filter for such a low frequency, were very large inductors or reactors and very large capacitors. At least that's the way my group leader suggested that I do it. But fortunately, I went home and was thinking about it, and I remembered that I had studied what was called a twin-T amplifier, which was only made of small resistors and capacitors, but it was a very elaborate circuit. And a twin-T bridge, I should say. And I got the idea of using this bridge in a feedback, vacuum tube feedback circuit to amplify the filtering capabilities. And so I told my group leader about it, and he said, "Sure, try it." And so I built this circuit, and it worked beautifully. And then I was asked to make improvements on alpha ray measurement and detector and measurement instruments, which were used widely on various sites on the project, including the ones that I was aware of were Monsanto and Dayton, where they were manufacturing polonium for the trigger for one of the bombs, and also Mallinckrodt Chemical, where they were processing uranium, and of course Los Alamos, where they were plutonium and other things were like polonium and other things, all needed alpha ray measurements. So I fortunately was able to develop an improved system for this purpose, and as a result of that, and because of the wide, we had a production line also at the instrument section at the Met Lab, which produced instruments that we developed for distribution to the various sites. And I was then appointed liaison to train people on the use and maintenance of the equipment which I had developed. So I traveled to all of these sites quite often. And on my first trip to Los Alamos, I boarded the train in Chicago at 3 o'clock in the afternoon. Or maybe I told this yesterday. Did I? Oh, okay. Then I won't repeat it. Oh, I have just one anecdote. I had been a magician in my high school days, and it was on my Army record. So one day I received a phone call from the Army office, and they said, Sergeant Schoke, the officers we're having a Christmas party here at the Armory where the headquarters was near the University of Chicago, and we'd like you to. Are you still doing magic? And I said, well, I haven't done it for a while. Well, yeah, could you do it? And I said, oh, I guess so. Well, we'd like to have you perform at the officers' party. So I went for that Christmas party, and I performed, and it was well accepted. And so the following year, I was requested to come again. And I noticed when I got up to perform that there were about half the number of people and very few Army officers in uniform. Very few. And I wondered what happened. Well, and I performed, and that was well. And then I went, a couple of weeks later, it came out that a rumor had circulated just prior to Christmas party that the Germans had succeeded in getting an atomic bomb and were going to drop it on Chicago. So you can guess where the officers were. Thank you.
Last but not least, Norman Brown.
Well, a couple of things that have been mentioned reminded me. A friend of mine said that he heard somebody say that the reason the Germans never got the bomb was because they didn't have Leo Szilard. And I think there's a lot of truth in that, frankly. The other thing is the mention of polonium also brings to mind the fact that was used as the trigger for the...
Yeah, with beryllium.
Yeah, this is one half. This was made in the mold that made the plutonium core for the first few bombs. So that's how big it was, a sphere this size. And the little hole here was for the polonium trigger. So that was the size of the sphere.
Polonium.
Yeah, polonium. And this is made in that mold from pieces of the fused glass from the bottom of below the tower that the Alamogordo test was done. And some of the GIs collected a big cardboard box full of the fused glass that was on the ground before the Army restricted collection. And a bunch of us bought pitched in to buy powdered lucite. And so the metallurgist who formed this hemisphere of, it was uranium, it should have been, but anyway, it was lucite, embedded some of the fused glass. And this was a paperweight. A paperweight. Yeah. And the same thing, but it was just made as a paperweight and pieces of the fused sand.
From Avogadro?
Yes. The other interesting thing about these things, that one day in, what was it, 1993, we went to Los Alamos to visit some of our relatives who were working there. What? 2003. Sorry about that. And when the museum opened, we went in, and they had some of these pieces of fused glass. I can't remember whether they were embedded in lucite as these are, but in any event, and they were all gray. There was no color to them whatsoever. And in the course of our visit there, somebody urged us to talk to the director of the museum. And so I mentioned to him that I had much prettier samples of the fused sand with all color, whereas the ones that they had on display in a case, glass case, was all gray. And I said, I'm willing to sacrifice one of these things if you would like to put it on display. And he said, oh, anything we get like that, we don't put on display. It goes in a secret room. So that was the end of my offer. The other thing that I want to mention, this is supposed to be a story of innovations. Well, I had a security innovation in that everything that was shipped in from Hanford, which was plutonyl nitrate, which is a solution of plutonium, a plutonium salt, came to me. I cannot remember how I was selected to receive these, but I got these samples. It was a big liter flask, and I had to sign a receipt for how much was in the sample that Hanford had sent, how much they claimed it was in it. And I took a tiny little sample and sent it for radioassay to see how much was really in it. And I would get the results back, and it was always less than Hanford had said they had sent. And so I started making a chart, and the date, and how much Hanford said they sent me, and how much I sent out for assay, and how much they said it was, and what was my back calculation to see what was in Hanford's flask after all. And then near the end of the line, we put it through a purification process, and then it went off to dry chemistry for further operations. And so I had this, and I did this for every single sample that came in, and by date. So by the time I got to the bottom of the chart, it was a complete history of plutonium shipments into Los Alamos and what happened to them when they left the wet chemistry group. And then, of course, it was an extremely secret document. So I would stamp it secret, and then I couldn't look at it anymore. I didn't have a secret clearance because the criterion for a secret clearance was to have a bachelor's degree, believe it or not. So I was cleared only for confidential papers. But if I needed to see a secret paper for, I was working with chemistry, I would go to somebody who had a secret clearance and ask him to get it out of the library for me. He would get out of the library. I would read what I needed to read. I'd give it back to him, and he'd send it back to the... So that was the security innovation that I was in charge of. After Los Alamos, well, first of all, I must say that before I left and was discharged, I was asked by Art Wall to come to Washington University at St. Louis, where he was teaching. He was going to go back to teaching after he left Los Alamos, and so I went back to MIT, got my bachelor's degree, and I called Art and said, no, I don't think I'm going to get involved in nuclear chemistry anymore. And I first went to work for GE, and the sequence, I got the reputation as a butterfly because every 5 years I changed my career, and I ended up working at the National Academy of Sciences and the National Bureau of Standards, which it was called then. It's the National Institute of Science and Technology now, I think. And I worked at the, I don't know, I'm repeating myself, please forgive me. I worked at the National Academy of Sciences for a while, and then I decided that I really would like to do something that would be good for people. And it was at that time that Janet and I were married, and we began to have children, and I kept thinking, you know, if my children were starving, you know, what would I like to do? So then I began working in food technology and technology and resources for renewable technology and resources and food problems for developing countries. And from then on, you know, it was just a succession of things. I worked for USAID. I went to work for the Department of Energy, thinking that I was going to be doing something useful in terms of renewable resources and renewable technology for developing countries. But the powers that were at the time had different thoughts and refused to allow me to work on something for developing countries. By that time, I had done a lot of traveling in the developing world when I was working for AID, and the people at the Department of Energy wanted me to model a program for developing countries and then use it in every developing country. And the people said this had never been in a developing country, so they had no idea that they were all different. In any event, eventually I retired and began consulting and did my consulting for organizations like the World Bank and the Asian Development Bank and AID. I designed programs for AID. And eventually, I just plain retired. I built my first computer in 1985, and I've been hanging out on computers ever since, and I spend my time deleting thousands of emails every day. And it's not a bad occupation. Thank you very much.